What are you looking at here? This is a robot dog balancing on a yoga ball, traversing the sidewalk. How is this possible, you ask? Let's find out. Now, this may not necessarily look too impressive to you who watches the sci-fi movies, but in the world of real-world robotics, this is actually quite impressive and unprecedented. But before we get started, if you don't know me, I'm Chango, and I am your next-door autistic femoid. You might have also known me as an early contributor to the early days of the Cosmos Network. And I've been pretty quiet this year, but now I'm ready to come out with my new podcast series, which focuses all on robotics. Yes, you heard that right. I have a new passion. I have actually pivoted out of crypto and into the world of hardware. I'm going to read white papers covering the state of the art in robotics because this is my new passion and I just want to share it with you. So we're going to cover 4 important papers. And the first one is called DrEureka, which is the research by Google DeepMind behind which enables this little quadruped to be walked while balancing on a yoga ball. And then the next one, we're going to talk about Voyager and then Sakana AI's Darwin-Gödel machine, as well as another DeepMind research called AlphaEvolve. This is a 2-parter, so it's not, we don't want to make it too dense. We're going to make it lightly digestible for you. DrEureka is written by a couple of authors, namely Jason Ma, and Jason Ma is one of the co-founders of this new foundation model project called Dyna. Mechanism Capital just announced that they led the Dyna round with Jason Ma, the lead researcher that co-authored this paper. So that's why I'm quite bullish on Dyna. Now, caveat here with this paper is that I've asked independent robotics researchers, and yeah, they said that this research has not been completely replicable. That being said, it is still groundbreaking. The TLDR behind Eureka is that they've been able to create a simulation in a virtual environment that brute forces reinforcement learning into a robot in a contracted amount of time. Okay, first of all, a foundation model as opposed to a large language model is just a framework that trains an AI on modalities other than language. It would be visual data, tactile sensing inputs, and any other inputs for that matter. Reinforcement learning is a learning paradigm that teaches an AI how to do a specific task. In the reinforcement learning used in fully self-driving vehicles, for example, they use something called scalar rewards and basically attribute positive or negative rewards from the AI doing a certain action. So a lot of it is collision prevention. You give the AI a negative reward to train a piece of hardware not to run into things or kill people. Another example would be if you're training a humanoid robot to chop fruit. That task takes more than 1,000 hours in order to train an AI to do this like really menial, repetitive task that is really easy for you and me to do. 1,000 hours is the equivalent of a 3-year-old. So if you don't have 3 years to train a robot to just do this, even after you train it up, just reinforcing this action, it still does it at about a 60% confidence rate. And so like, what does that learning curve look like to get it to 100% confidence, just to like make sure that it is really going to chop fruit reliably every single time and not throw a knife at you? We don't know what that upper bound is. But with DrEureka, what they've done is they've created a simulated environment such that it contracts the amount of time it takes to perform reinforcement learning for a robot to do any task. And so it's because it compacts the amount of time within a simulated virtual environment, and then it just hyper repeats that same training over and over again, just like they did this with the quadruped. And then the unlock is that they're able to transfer the simulation into IRL. And what you're seeing in this video here is the result of that research. terrain robustness. On the quadruped locomotion task, we also systematically evaluate DrEureka policies on several real-world terrains and find they remain robust and outperform policies trained using human design reward and DR configuration. I mean, yeah, he's helping it a little bit by holding it on leash, but still, like, it's an expensive piece of equipment. So, like, if it falls, they don't want it to get broken. Most people can't do that. I can't do that. You'd have to be a gymnast to do that. They've even generalized it such that the dog can correct for edge cases and anomalies, such as the ball getting deflated as it balances on it. So it's learning and adapting as it goes, just like a human would. And it closes out with a note on failure videos and limitations. So finally, we show several occasions when the robots fall from the ball. There are many avenues to further improve DrEureka. For example, its policies are currently entirely trained in simulation, but using real-world execution failure as feedback may serve as an effective way for LLMs to determine how to best tune sim to real in successive iterations. Furthermore, all tasks and policies in our work operate purely from robots' proprioceptive inputs, and incorporating vision or other sensors may further improve policy performance and LLM feedback loop. The next paper that I'm going to cover is Voyager, and this one's interesting to you if you're a Minecraft lover. Voyager is an open-ended embodied agent with large language models, also placed in a simulation. So the TLDR of this is someone put an LLM inside the world of Minecraft to simulate gaming it. So it puts an intelligence and AI into Minecraft to do various tasks to basically help it learn to better have a generalized intelligence to be able to extrapolate to do any conceivable task in the future. So we're going to read the abstract. We introduce Voyager, the first LLM-powered embodied lifelong learning agent in Minecraft that continuously explores the world, acquires diverse skills, and makes novel discoveries without human intervention. Voyager consists of 3 components. 1, an automatic curriculum that maximizes exploration, an ever-growing skill library of executable code for storing and retrieving complex behaviors, and 3, a new iterative prompting mechanism that incorporates environment feedback, execution errors, and self-verification for program improvement. Voyager interacts with GPT-4 via black box queries, which bypasses the need for model parameter fine-tuning. The skills developed by Voyager are temporally extended, interpretable, and compositional, which compounds the agent's abilities rapidly and alleviates catastrophic forgetting. Empirically, Voyager shows strong in-context lifelong learning capability and exhibits exceptional proficiency in playing Minecraft. It attains 3.3x more unique items, travels 2.3x longer distances, and unlocks key tech tree milestones up to 15.3x faster than prior state of the art. Voyager is able to utilize the learned skill library in a new Minecraft world to solve novel tasks from scratch, while other techniques struggle to generalize. So basically, the quote state of the art in generalized intelligence is not that good. They can't really perform generalized complex tasks over a long span of time. But what Voyager has done is an experiment attempting to create a framework that allows LLMs to do generalized work and adapt to complex and changing environments. So the introduction: building generally capable embodied agents that continuously explore, plan, and develop new skills in open-ended worlds is a grand challenge for the AI community. Classical approaches employ reinforcement learning and imitation learning that operate on primitive actions, which could be challenging for systematic exploration, interpretability, and generalization. Recent advances in LLMs-based agents harness the world knowledge encapsulated in pre-trained LLMs to generate consistent action plans or executable policies. They are applied to embodied tasks like games and robotics, as well as NLP tasks without embodiment. However, these agents are not lifelong learners that can progressively acquire, update, accumulate, and transfer knowledge over extended time spans. Let us consider Minecraft as an example. Unlike most other games studied in AI, Minecraft does not impose a predefined end goal or a fixed storyline, but rather provides a unique playground with endless possibilities. An effective lifelong learning agent should have similar capabilities as human players. One, propose suitable tasks based on its current skill level and world state. For example, learn to harvest sand and cactus before iron if it finds itself in a desert rather than a forest. Two, refine skills based on environment feedback and commit mastered skills to memory for future reuse in similar situations. For example, fight zombies. Or three, continually explore the world and seek out new tasks in a self-driven manner. So this is the knowledge graph that encapsulates how the LLM is learning. So this is pretty reasonable. You have a task and then its reasoning skill using GPT-4. And so if we go through one example, the task would be craft one stone pickaxe. The reasoning behind it would be, okay, check your inventory first. You've got oak planks, 4 sticks, crafting table, stone, wooden pickaxe. And the reasoning is such that since you have a wooden pickaxe and some stones, it would be beneficial to upgrade your pickaxe to a stone pickaxe for better efficiency. And it goes on, like so on and so forth, with like all these different varied tasks. Minecraft is a great simulated environment because it's a sandbox, just like in the real world. So if you extrapolate Voyager to be applied to the real world, you could have LLMs performing any such complex tasks, provided that it understands what its inventory and resources are, while equipped with the set of reasoning skills to allow it to complete a task. Conclusion. In this work, we introduce Voyager, the first LLM-powered embodied lifelong learning agent, which averages GPT-4 to explore the world, continuously develop increasingly sophisticated skills, and make new discoveries consistently without human intervention. Voyager exhibits superior performance in discovering novel items, unlocking the Minecraft tech tree, traversing diverse terrains, and applying its learned skill library to unseen tasks in a newly instantiated world. Voyager serves as a starting point to develop powerful generalist agents without tuning the model parameters. That's Voyager in a nutshell. We'll have to see if it has any outcomes for robotics and applications in the real world. That's what I'm particularly interested in seeing. Overall, this is very exciting stuff. This is state of the art as of the last 18 months. So the fact that you're keeping up with this research and white paper reading means you're essentially ahead of the curve. Who knows how contracted this is going to enable AI and robotics development in the future. If between the two of these, Voyager and DrEureka, it unlocks consumer robotics within the next few years rather than the next few decades. Now I'm going to pause here because that was a lot to take in. The second part is going to be more AI algorithms with respect to the Darwin-Gödel machine by Sakana AI and DeepMind's AlphaEvolve. Those ones are going to be interesting.